at each stage you figure out which edge has the smallest weight and doesn't form a cycle. Alright, so what is it supposed to solve? It's supposed to output a spanning tree of minimal weight. Okay, so that's what the algorithm is supposed to do. So to show that it works, we have to show that the output is indeed a spanning tree of minimal weight. So just a reminder, a tree definitions. A tree is a graph with no cycles. A spanning tree is a tree inside a graph that contains all the vertices of the graph. So that the tree, it's a connected graph. That's important. So a tree is connected and acyclical. Spanning tree, you have a graph, you pick some vertices, you pick some edges. That forms a subgraph. If that subgraph has all the vertices, uses all the vertices of G and is a tree, that's a spanning tree. And then minimal weight just means that among all the spanning trees, consider the sum of the weights of the edges, which one has the smallest sum. Okay. And the spanning tree of minimal weight is not necessarily unique. So if you have two edges that measure the same, sometimes you can make a switch in your tree and still have a minimal weight spanning tree. So let's look at, say, the following pseudocode. All right, so you start with the empty set, and you have an empty tree, and then you do while the size of S is less than N. So let's say your graph G has N vertices. So then you add edge of minimal weight. It doesn't form a cycle. So I guess we could say let E be an edge of minimal weight that doesn't form a cycle, then you add, let's say, E and comma B. So now S will be whatever S was before, and you add these two things to S. And T will be whatever T was before, and you add the edge. So that's the code, and a few questions are, does this code finish running? And two, does it give you the spanning tree when it's done? When you exit this while loop, you return the tree. Right, so T will be your tree. Okay? The two questions are, does this code finish running? I guess sometimes the word used there is halt. And the second question is the output a minimal weight spanning tree? Okay, so why would the code stop running? So let's first answer the first question. So suppose the code keeps running, like enters an infinite loop. So if the first question is, does it finish running? So does it halt? How could it not finish running? That could happen if this while loop you just never reach end, right? So that's how it could run forever. So let's suppose it's running forever. So the size of S just never reaches N. So S is less than N. And somehow it's not adding vertices, right? So when you consider edges of minimum, like, so if you consider edges, the only way this stays put, so okay, let's see. We can say let M be the largest number such that size of S is N. Okay, so you keep running that, and at some point it gets stuck, right? So how do I know it gets stuck? Well, this process either adds some vertices, so the size of S grows by 0, 1, or 2. It never goes down, right? So it either stays at some level or it goes up a bit. So if it doesn't reach N, it means that it went up, but it stopped at some moment before N. Right? So let's call that moment M. Okay? So then, now consider edges of the form A comma B with A in S and B not in S. Okay, now how do we know that these edges exist? Okay, so why do we know that these edges exist? I'm thinking of considering something that might not even exist, right? How do we know that they exist? So to find this minimal spanning tree, your initial graph has to be connected, right? So if the graph is connected, that means that from any point, any two vertices in the graph, there's a path connecting one to the other. So you can imagine you have like this big graph G, and S is inside G. So there has to be a path connecting some edge in here to some edge outside of it. So because there's a path, at some point you can look at the last thing that's still inside S and the first thing that's not in S. And that would be of this form. Right? There is like something that is in here, not in there, and there's that edge. So the algorithm says you grab the smallest edge in weight, right? That doesn't form a cycle. But if you have something in S and something not in S, this AB does not form a cycle. Right? Because to form a cycle, you have to like go back to yourself. So that last edge would have to be two things in S. So once you have something that's with a coordinate that's not in S, that can't form a cycle, and if you now just add, let's go, so this would be A, that would be B. So now if you just add this edge, S grew up in size, and that contradicts that M was the largest. All right, so this process, when, like, it has to reach S equals M. It just can't stop before, because the graph is connected, so there's always some edge. Okay. Now, kind of what I proved here applies more to Prim's algorithm than to Kruskal, because with Kruskal the edges are first sorted and then you start putting them in, right? So it could happen that this edge was just not picked. That is like a super, well, let's think. So this isn't quite a proof yet, although this proof works for Prim's algorithm. It doesn't quite work for Kruskal. A reminder, in Prim's algorithm, you start with a root, then you look at things connected to it, and you grab the smallest one. And now you have two vertices, and you look at the smallest connected to those two, and you add that. And you keep building the tree. So this exact construction would show that that process keeps going until you covered all the vertices. Like this exact proof works there. With Kruskal, doesn't work because you sorted the edges first. So you could have this like bad luck where every edge connecting something from S to outside of S was already discarded. Okay? But then think about, how could an edge be discarded? It can only be discarded if it builds a cycle. But this edge could not have built a cycle by construction. So once you add that information, oh, these guys cannot build a cycle, so they could not have been canceled. So at some point you reach it, and at some point you draw that, so this process never ends. This process has to end. Okay? So this question is now answered. This code will finish. It'll return something. All right. Now the next question is what it returns a minimal weight spanning tree? By the way we constructed it, at no point does it have, all right, so now the second question. Is it a minimal weight spanning tree? Okay, so the minimal weight spanning. So by construction, T has no cycles, right? So we only added an edge if it avoids a cycle. So whatever you have at the end has no cycles. That's a good sign. The next question is it connected? Well, all right, let's not add connected yet, but is it spanning? Yes, because it has n vertices. So spanning means that all the vertices of the graph were used. The graph has n vertices. This only stops when you have more than n, well, at least n vertices. So it'll stop when you have exactly n. So that means it'll be spanning. So we have minimal weight spanning tree. So we know spanning. And then tree means no cycles. And it means connected. So no cycles we have confirmed. Now, is it connected? All right. I'm thinking of something like so if you have that graph and you follow Kruskal's algorithm, that just gives you these, right? And that's not connected. We're done. So, as written here, this doesn't work. Okay, all right. Oh, that's annoying. kind of nuts. So maybe I'm missing a step. All right, so my apologies. You're looping on the set of edges instead of on the set of vertices. So that was a mistake. So if you loop on the set of vertices, then this situation can happen. So you don't get a connected thing. Okay, so then at the end of the day you have n minus 1 edges. So the Kruskal algorithm will create n minus 1 edges. Yeah. So I guess in some sense you don't even need to keep track of the vertices. But. Alright, so this proof I guess works for Prims. Doesn't quite work for Kruskal because Kruskal focuses on the edges, not on the vertices. So if you focus on the edges, how do we know that thing ends? And I guess the key is that you can get up to n minus, you can surpass n minus 1 edges if you're going to avoid cycles. So if you don't have cycles, the most number of edges you can have is n minus 1. Once you have n, you can use the pigeonhole principle to show that there's a cycle, a loop. And so now that because we know, so I guess here it's more, is it spanning? Yeah. So here the order should be the other way. It'll be, is it connected? And here we have n minus 1 edges. And no cycles implies we reach n vertices, so everything is connected. And then once we have all of this, is it spanning? Again, yes, because we reach n vertices. So if you think about this one here, if we follow that algorithm, then x edge to draw is that one, and you do get a tree. All right. So the way I wrote the algorithm before, you kind of stop prematurely. Once you covered all the all the vertices you stop, but actually if you do that, you're not gonna have it connected. So now we know it's a spanning tree. The question is it minimal weight? So let's prove it's minimal weight. All right, so we have the TK be the tree that Kruskal outputs. All right, suppose it's not a minimal weight spanning tree. So I guess we should point out that there is a minimal weight spanning tree. How do we know that? Well, TK is a spanning tree, right? So we know spanning trees exist. So if you grab the set of all spanning trees, at least one of them has minimal weight, right?
Mm-hmm.
They're all, the weights are all positive integers, so you have to get a minimal weight. So there exists a minimal weight spanning tree T. So by construction, well, by assumption, T is not TK, because we're saying the TK is not minimal weight. Alright, so by assumption T is not TK. So let the edges of TK be E1, E2, to En minus 1 in order of length, sorry, of weight. And then we grab T, and we do the same with T. So let E1 prime, E2 prime, En minus 1 prime be the edges of T in order of weight. All right, so since T is not the same as TK, there exists minimal I such that EI is not EI prime, right? So so we would have E1 equals E1 prime, E2 equals E2 prime, EI minus 1 equals EI minus 1 prime, and EI is not EI prime. So there's, at some point, the trees are not the same anymore. So, a few classes ago, when was it? The midterm was Monday?
Yes.
So last Friday, we proved a few things. So if you add an edge to a tree, it creates a cycle. And we also proved that if you remove an edge from a cycle, Well, I don't remember if we proved this one. It does not. If you remove an edge from a cycle, it does not disconnect the graph. So if you have a connected graph and it has a cycle somewhere, and you remove one of the edges, you're still a connected graph. Another statement we didn't prove is a tree with n vertices has n minus 1 edges. We didn't prove this one, but it's pretty intuitive. If you think of a tree, you could think of so if you have like a tree, then like each element has like a parent, unless they're a leaf, right? But then there's an edge between them and their parents. Or alternatively, probably an easier way to see it is a node is in a tree. It has to have an edge connecting it to something, right? So there's sort of like an edge for every vertex, except for the first one, because you would be double counting. So there's n minus 1. Go from the root. From the root you have some children. So for each child of the root, you have an edge. And then for each grandchild, you have an edge. So each new vertex you're creating came with an edge, but only one edge, right? Because there's like a hierarchy. So other than the root, every vertex is associated to a root from which it arrives. So if you have n vertices, you have exactly n minus 1 edges. All right. So now why does Kruskal's algorithm give us a minimal weight thing? All right, so let's insert EI in T. Okay, so again, we have T is a minimal weight spanning graph. TK is the one that came from Kruskal. So we check, is the smallest edge on one the same? Yes, what about the second smallest? What about the third smallest? At some point, you finally get somewhere where they differ. They're not the same. So what we're going to do is we're going to grab EI, insert it in T. Okay? Once you insert EI in T, now T will have a cycle because of this. So now T has a cycle. All right? So in this cycle, this cycle must have an edge which we'll call F, that is not in TK. Okay, so why is that? Because if we inserted EI into TK, we have no cycles, right? So if it created a cycle in T, it created a cycle because there's something that's in T that's not in TK. So let's call this edge F. So now let T prime be T, you add EI, and you remove F. So it's the tree where you add this edge that was in TK, but you remove the thing that that's in the cycle. After you added this and created a cycle, take an element out so that it doesn't have a cycle anymore. All right, so T prime is connected because of 2. All right, so it's connected. T prime also does not have a cycle. Does not have cycles. Because T didn't have cycles, and when we created a cycle, we broke it. So there's no cycles, right? The only possible cycle, we just broke it by removing it. T had no cycles. And by removing F, after adding EI, blah, blah, blah. All right, so that means that T prime is a tree, right? Now note that because Kruskal grabs edges in order of weight, that forces that the weight of EI is smaller than the weight of F, right? Because if the weight of F was smaller than the weight of EI, then you could have just grabbed F to begin with, and it wouldn't form a cycle because T prime has no cycles. So we could have picked F instead of EI in the Kruskal algorithm. All right? But on the other hand, because T has minimal weight, well, let's see what is the weight of T prime. So the weight of T prime is the weight of T plus the weight of EI minus the weight of F. Now, because T has minimal weight, the weight of T is at most the weight of T prime, right? So T is minimal weight, so if you pick any other spanning tree, it has to have bigger weight or equal. But the weight of this is easy to calculate. You calculate the weight of T, then you add the weight of this edge, then you subtract that weight. But because of this inequality, that means that this subtraction is less than or equal to 0. So we've shown that the weight of t prime is greater than or equal than the weight of t, but smaller than or equal than the weight of t, the only way this could happen is if t prime has the same weight as t. Okay? All right, so now how do we proceed with the proof? Well, now the edges in order of tk and t prime are the same for E1, E2, ei. Right? So it's one longer than when you compare t to tk. So now do this process again. You find the first location where they're different between tk and t prime, and you build t prime prime. And now the weight of t prime prime. So repeat the process. And we have weight of t prime prime equals weight of t prime, and tk and t prime prime match at least I plus 1 terms. And then you keep repeating, and now you have at least I plus 2 terms, at least I plus 3 terms. Eventually you get to at least n minus 1 terms. So they're the same tree. So at some point by these replacements, you get the same tree, but all of these guys have the same weights, and that weight is the minimal weight. So you finally conclude that the weight of tk has to be the weight of t. Okay? It's pretty crazy, but the algorithm actually works. What surprises me the most about the algorithm is that you end up connected at the end, even though you're just picking edges all over the place. But that just happens because of once you reach n minus 1 edges, you have to be connected. So it's a surprising algorithm. I think Prim's algorithm is a little easier to prove that it works, just because when you're constructing it, you're forcing the tree and you're picking it with minimal weights. It's still not, I mean, this type of stuff is from an area called combinatorics, and one of the things that's difficult in combinatorics is how do you know that maximizing locally will give you the maximal overall? That's one of the hardest type of problems in math. And so it's kind of, that problem is when does the greedy algorithm work and when doesn't? And proving that the greedy algorithm works in the settings where it works is usually pretty hard. So as you can see, we've worked pretty hard to show that the greedy algorithm, aka Kruskal's algorithm, worked. And often there's this balance in math and in computer science where we know how to do the solution locally. Like this is very common in, what's it called? Like in deep learning things where you're at a location, you want to get the max, and you calculate the gradient and then you travel in that direction. But then you can find a local maximum that might not be the global maximum. So this kind of situation happens all the time, and then proving that the optimal path, so if at each stage you do the optimal step, then it seems like at the end you optimize things. But that's not always the case. Right? So again, the classic example is if you have like a graph with 2 peaks, if you're here and you optimized in which direction you walk steeper, then you walk in that direction to get there, and you didn't actually reach the peak. So if you're optimizing with your surroundings, you often don't get the optimal of the global path. So This is one of the combinatorics is, that's one of the difficulties of it. Proving that something is actually optimal. And here you get a taste of it. All right, have a nice weekend. See you Monday. When's the homework due? Next Wednesday?
Homework due for CS270?
For
270?
270? No.
There's only 8 months.
Yeah, he said you don't have to do anything. He said you can do it if you want. I'm not doing it.